Hi guys, this is section 7.1 part 3. Just before we get over into the cloud and take a look at RStudio, I thought we'd take a look at the back page, second page of the examples handout I had that I was looking at earlier. And it kind of fixes some ideas that we've been getting at with the sampling distribution. This is a sampling distribution shown for the proportion of U.S. citizens over 15 years old who have never been married, using the data from the 2010 census and random samples of 500. So pretty large sample sizes. Taking samples from the census, which is the population. So what does one dot represent? One dot is going to represent the proportion of U.S. citizens over 50 years old in a sample of size 15. So let me see if I can quickly type that in. It's the proportion of U.S. citizens over 15 years old who have never been married in a sample of size 500. Okay, I know. Let's see if we can straighten this out a little bit. There we go. It'll fit more or less in there. Okay. So it's of samples of size 500, the proportion who have never been married. All right. So use the sampling distribution to estimate the proportion who have never been married. Give correct notation for your answer. So from before, we said that it should be somewhere in the middle, right? That this sampling distribution is going to be centered around the true value, and I suppose that seems to be as good a guess as any. So if we take p hat equal to 0.32, that doesn't seem too far off. If we take a random sample of 500, compute the proportion, how likely is it that we will see that that result for each sample proportion below? So the idea is, how likely is it that we'd get 0.3, or something like that? So that's quite likely. So we'll say that that's a plus. That's going to be something very likely. How about a 0.37 or 0.2? Well, 0.2 would be way out here. That would be not at all likely. 0.37 is, well, maybe not very likely, but it could happen. So a small chance. We're not going to quantify this yet. 0.74 ain't going to happen. All right, that would be way out here. So based on this sampling distribution, this is the kind of thing that would never happen. Estimate the standard error of the sampling distribution. How in the world can we do that? Well, so here's the idea where we think about the 95% rule. So if we take something like this and something around here and say that looks like about 95% of the values of p hat. Right, there are a few over here that are excluded, a few over here, but all these of these many different samples, okay, looks like that would contain about 95% of them. So we'd say that there were 95% are between about 0.27 and about 0.37. So if this range x bar plus or minus 2s contains 95%, we've said, if we start here at 0.32, that 2s range is about 0.05 on either side. So 2s is around 0.05. So that means s is around 0.025. Might not be exactly right, but it doesn't seem like too bad a guess. So that would be our guess, around 0.025. Okay, and again, it was from eyeballing the 95%. All right. If we took samples of 1,000 instead of 500, would we expect that to be more accurate? Well, I'd say more accurate. Larger samples are going to be more accurate. Would the standard error be larger or smaller? Well, more accurate means less variability in the estimates, so it would be smaller. Okay, and then this last picture takes us through and asks us to try to determine which of these correspond to which sample size. So the idea here is thinking about what's happening to the variability in the estimator as the sample size gets large, or in these statistics as the sample size gets large. Well, here's the basic principle. As the sample size increases, the variability decreases. So as n gets larger, we get closer to the corresponding parameter. Standard error gets smaller. So going back here, here, we would say that this one with the most bunching would be n as 400, and the most spread would be n of 25, and the one in the middle would be n of 100. Okay, so now we should be set to understand the idea of sampling distribution. So let's go in and take a look at using R in the cloud. Now I have some files here that really it's just one file. It's the RMD file, and then when you knit it you'll get the PDF file. I'm going to click on that, and I'm going to suggest that we can pop it out here. Now this is for all of chapter 3. Right? So we're going to continue to work through this through all of chapter 3, confidence intervals. Section 3.1 is sampling distributions with R, Mosaic, and ggplot2. Okay, so here's the deal. We're going to work our way through this. This is going to illustrate a variety of things. It's going to illustrate how to simulate the sampling distribution. So we're going to be thinking about sampling from a known population. Okay. Now, I'd like to work through here, that is in this window, rather than jumping back and forth. So what I'm going to do is run commands as we go through here. I loaded the libraries. These are more relevant if we're actually knitting, but I'm going to run it. One thing, I don't use this too often, but the cache equals true as an option up there will save results from simulation as we go, so it'll just speed up some of the calculations. It won't have to redo everything every time we kind of run stuff from a particular chunk. Okay, so the key idea is to get into this idea of sampling variability. And I've talked about these ideas already. These are just introducing notation. So let's get into an example. And I've keyed these to examples in the first edition of the text. I haven't gone back to verify that they fit with the current edition, but I think you'll get the essence of it anyway. That is understanding what's going on, because you can always look up these data sets by using question mark statistics PhD, and that'll explain in the help from R what these data sets are. This is for graduate schools, and let's go ahead and run that. So here are the universities, corresponding departments, and the full-time enrollment. So each of these universities has a value and enrollment, and so what we're going to be trying to make inference about is the average grad enrollment in statistics or biostatistics departments in the country. So we're going to first take these 80-some schools, I think it is. Let's see, where did it go? I'll run it here, dim of statistics PhD. Let's see, 82, yes, 82 different schools. So we'll run that again. So the mean of all of those is what we get here. Okay, so this is mu, 53.5. This is the mean enrollment, and that's how you could write mu in your output. Example 3.5 now is to select a sample. So we're going to use the sample function, which we've seen before. I'm going to sample from this data set and take a sample of size 10 and see what happens. So we run that, we get a sample of size 10. Here's what it looks like. Yours will be different from mine, right? This is random, so we're not necessarily going to get the same sample. You'll see the enrollment and the original ID, what row it was in originally. And then we get the sample mean, 32.2. You run it a few more times, you'll see that number changes from sample to sample. It's expected, it's sampling variability, right? Okay. Now, note that this sample has been assigned a name to which we can refer back to find the mean of that particular sample. So I gave it the name sample 10, and then I found the mean for data equals sample 10, not for statistics PhD. Alright, now try running the following R code several times to see how it changes. So I just put that all together on one line rather than saving it each time. But once again, you can see that it varies because of sampling variability. So now we're looking at simulating the sampling distribution by sampling from a known population, this population of 82 graduate schools. But now here's where we're going to learn something new. Alright, so make sure you pay attention. This is a construct we're going to use in R extensively as we go through. Now it's something that comes with the Mosaic package that makes our simulation work easier, and it's the do command. So let's see how do works. Sample distribution, we're going to store. We're going to use that to store the results. So we're going to do something 1,000 times, and that is eat a bag full of M&Ms. Now that would get a little bit much. But we're going to sample from this population of statistics PhD. So notice our data is sample statistics PhD 10. So we're doing the sampling on the fly here in the data equals command. You're not going to have to do these from scratch, so we're using these as templates, but you will occasionally do something like this in the homework. But this asterisk has to be there. There's no tilde here. There are tildes elsewhere. But do, and how many times, and then what are you going to do? And the sample size comes over here. So let's run this so you can see what's stored in the sample dis command is called mean. It's the sample mean, so the X bar values for the first 3 of 1,000. This thing contains 1,000 values of X bar. So let's see what it looks like. Well, not surprisingly, it has a bit of a bell shape. Let's do it again just to see how stable that picture is. So rerun the sample, get a new picture. So you can see it has that general shape to it. Whether it has a little skewness or not, I'll let you decide. But this is our sampling distribution. So for many, but not all, the sampling distribution will be unimodal, symmetric, and bell-shaped. Okay, so let's carry on. This was the sample mean. Now let's go back to something like the M&M case where we're going to sample a proportion. A yes or no. So yes or no is like flipping a coin. So the Mosaic command for simulating a yes or no binary variable, like is the M&M orange or not, is the rflip command. So we're going to use that to simulate yes or no kinds of variables, as if we were flipping a coin with a specified probability of heads, in this case yes. Hence we could model a random sample of 200 individuals from a population where the true proportion is p equals 0.275 by simulating 200 coin tosses with that probability of getting heads. Now it would be hard to construct a coin that had that property, but we can do it by computation, by simulating. So let's run this a few times and see what we get. Well, there was once. I can run it again, see what changes here. Okay, you can see the number of heads changes a little, proportion changes. You see we're actually getting the string of results that actually occurred. Okay, so it's quite visual. Alright, so I ran it several times and noted how the string changed. But that's really not what we want to do. We want to just compute the proportion of the proportion heads, probability of heads, and use that. So it's set up to know to do that. rflip, and it plays nicely with do. So we're going to do 1,000 times this experiment. We're going to flip the coin 200 times, and this is representing a sample of 200 college education, I believe, with proportion 0.275. So let's go ahead and run that. And the head command is going to show us what this looks like. So 1,000 rows are in sample dist prop. That's storing the sampling distribution of the p-hat values. There's n, which is going to be 200 in every case. The number of heads, the number of tails. So 59 out of 200 gives us 0.295 for our proportion, our p-hat. So you can see these vary from sample to sample. But we also get the heads or the tails, so we could deal with that directly if we wanted. Let's go ahead and plot that. Now what we're plotting is a proportion. It's not a yes or no, though. It's quantitative because it's the statistic, it's the proportion that were orange, or the proportion who have some characteristic. We can see what it looks like. I always encourage you to do that a couple times and see how stable the picture is. Now notice there's some gaps here. Some of that is just an artifact of what happens when you divide the number of outcomes, a whole number, by another whole number. So there's a little trick I sometimes use, which is to use bin width as 1 over n. All right, 1 over 200 in this case, and let's see how that looks. See, that and actually ends up being quite a bit smoother. Let's try another simulation. Plot it here and then plot it down here, and you'll see that 1 over 200 smooths it out quite a bit. There's still a few gaps here and there, which are just due to randomness. But what it's doing is that every distinct value of p-hat then has its own bar in the histogram. But you see the general shape is pretty much bell shape. So why was 1 over 200 a good choice? Well, I just told you every bar has a distinct value of p-hat. Alright, so let's plug along. Now if you're getting a little fatigued here and just need to stop and think about this, I'd suggest that you pause and then rejoin me after you've had a chance to think about this. Okay, I hope you had a chance to get a cup of coffee or take a short break, because now we're going to plug along a little bit further to get to the end of this section. Quantifying sampling variability. So far we've generated samples and looked at them, but we haven't tried to quantify how much variability there is. But that's not difficult. Once we've got a simulation, we can use SD to get the variability. So recall that sample dist contains a sample means from 1,000 samples of the statistics PhD population. That's what we did up above. So if we run this, it will give us the standard error. It's telling us how much variability there is in the estimate of the size of the graduate PhD program. Okay, so that's a measure of the variability. I guess we ought to go back up and take a quick look at that, right? The mean was 53. Our estimates were 30 to 40 or so. And so here was an example. So 10 seems like a reasonable value for the standard error, and that was what we're getting, 10.9. Likewise, we can do that for proportion, and this was proportion with a bachelor's degree or higher, so that's what I was remembering. And so we get 0.03. And we can see that 0.03 is certainly a plausible value. Once again, you can look at the idea of being in the middle and then plus or minus at 0.275 and going plus or minus 2 standard deviations either side. And that's going to look like about 95% of the values. Right, as noted in the text, since these standard errors are estimated from a set of random simulations, the values might change slightly from one simulation to another, but it should still be close to 0.03. If you want the estimate to change less, you'd increase the number of simulations. If you want to make the standard error smaller, then the sample size is what would be changing. You'd need a larger sample size. Okay, you might have to think about that a little bit, the distinction between the number of samples and the sample size. Here, though, we're going to focus on the sample size, so we're going to repeat this for samples of 50, 200, and 1,000, and this will echo what we saw on the last page of the samples that we're looking at here, with 25, 100, and 400. doing a similar thing. This was with a quantitative variable. Here we're doing it with a proportion. So let's go ahead and run that, create our data sets, and now we're going to graph them. So we see the variability and the values for the various sample sizes. And if you look at the scale, you'll notice that here we're getting between 0.1 to 0.5 with samples of 50. By the time we get to samples of 1,000, the variability is much less than that. And that's what we would have predicted. Now we can also check that the mean doesn't change much. On average, in all of these cases, we're centered around the target, the 0.275, but what's changing is the standard error, the variability of our estimates. And it goes from 0.06 to 0.03 to 0.01. And here's an example of a simple table of results. So I'll show you what it looks like after we knit it here. But just notice that this is going to show different sample sizes and standard errors. I use this little trick of tick mark telling it here's some here's an R variable that's coming, and then close it with a tick. So this SE1 is actually going to read off the value that we just found up here in the simulation and put that into the table. It's not something we'll use a lot, but it's a powerful technique when you're writing an R report if you want to make it automatically update with the values that you get. So let's see where we ended off. Here were some of these simulated values. And here's what that table looks like after knitted to a PDF. It looks pretty slick. Use the R Markdown kind of commands for constructing that table the way I showed you from the table generator. And here's the results, and we see that the simulation gets smaller, and can see that those values correspond to what we got over there. What you'll notice when we do simulations is when you knit your simulation, you'll get a new set of values. So what you thought was a standard error is now suddenly different when you knit and submit it. We're not going to worry about that. We know that might change. But if you decide you want to try this technique of using the R command to refer to it by name, you can give that a try and let me know how that goes for you. Alright, so I think this is a place to stop for section 3.1. We've actually taken on quite a bit here. And then I will have warm-ups for you to try, and then a handed set for this that'll be due a couple classes hence. Alright, so thank you for listening, and let me know if you're feeling pretty lost about that. We can chat. We could even have a group of a few of us to talk and work through some of this. This is the kind of thing that's useful to talk through a little bit more in the large group, but I do usually walk the class through these simulations. But sometimes having some time to reflect and ask questions is useful. So take care, and I'll look forward to talking to you.